Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Aziz and I am from Hasanuddin University. Today I'm gonna represent Today I'm gonna presenting my video project that is entitled by Ordinary Differential Equation, Friedman Equations, and the Fate of the Universe. So first, we start from the very simple question that asked by Heinrich Schulberth. Why is the night sky so dark? Ancient humans assumed that the universe was unlimited in terms of space and time, and it is filled uniformly with stars in every direction. But if it's right, then logically, no matter where we look, our line of sight should eventually land on the surface of a star. That means the entire night sky should be blazing bright, just like the surface of the sun. But that is not what we see. The night sky is mostly dark. Then, why isn't the sky as bright as the sun in all directions? This is the essence of Olber's paradox, first proposed in the 19th century by German astronomer Heinrich Wilhelm Olbers. This paradox challenged the idea of a static and an eternal universe. But where did this logic go wrong? The resolution came with the rise of modern cosmology. In the 20th century, scientists realized that the universe is not eternal, it has a beginning, it is not static, it's expanding, and light from distant star hasn't enough time to reach us. In other words, the darkness of the night sky is not an absence of the stars, but a reflection of the universe's finite age and dynamic nature. This realization led cosmologists to abandon the idea of a static cosmos and instead explore a mathematical framework that could describe an expanding universe or a universe whose size changes over time. This framework begins with equations, powerful equation, the Friedman equation. Now, before we discuss more about Friedman equation, I'm gonna introduce the mathematical tools that we're gonna use to this project, that is differential equation. A differential equation is a mathematical equation that relates a function with its derivative. Differential equation describe the relationship between the rates of change of quantities and the quantities themselves. As a type of ordinary differential equation is a separable differential equation in which the variables can be separated on the opposite side of the equation. This allows for the equation to be solved by integrating both sides separately. Now, here is the general form, and here is the example of the separable differential equation. Okay, now we continue. If the universe, we back to the problem. If the universe is not static, then how exactly does it evolve? How does it expand, slow down, accelerate? Now, to answer this, we turn to one of the most powerful tools in physics, Einstein's general theory of relativity. This describes gravity isn't a force but a curvature of space and time shaped by the presence of matter and energy. Now, Einstein's field equation is defined by G plus lambda G is equal to kappa times T, while the Einstein tensor is defined as G is equal to R negative 1 over 2 times R times G. Now, these are a complex set of nonlinear partial differential equations involving tensors and geometry, but under assumption of cosmology that the universe is homogeneous and isotropic, those equations simplify dramatically. They reduce to a set of legend equations that describe the dynamics of the universe scale, that is, the Friedman equation. The first Friedman equations look like this. A dot over A squared is equal to A times pi times G over 3 times rho negative K over A squared plus lambda over 3. Meanwhile, the second Friedman equation that describe the acceleration or the deceleration of the expansion look like this. A double dot over A is equal to negative 4 times pi times G over 3 times rho plus 3p. This tells us how pressure and density slow down or speed up the universe expansion. Now, we're going to solve the Friedman equation. First, consider a universe filled only with non-relativistic matter, often modeled as pressureless dust. In this case, the pressure term is 0, and the universe density scales with the volume, or rho as a function of A is proportional to A to the power of negative 3. Substituting this into the first Friedman equation and assuming that the universe is flat, which is mean K is equal to 0 and has no cosmological constant, we get this. And if we're solving this equation, we will have another separable differential equation that if we integrating both sides, we will have that the scale factor or a as a function of t is proportional to t to the power of 2 over 3. Now, let's consider a universe dominated by radiation, such as the early universe. Radiation loses energy both from expansion and from redshifting, so the energy density drops faster, which is mean rho as a function of a is proportional to a to the power of -4. Now, again, by solving this, we will have another separable differential equation that is, if we integrating both sides with the same boundary, we will have a as a function of t is proportional to t to the power of 1 over 2. Now, what if we include the cosmological constant that is representing the dark energy? Then the Friedman equation will become like this. And we will solve the equation like this. But this form is more difficult to solve analytically. But numerically, it reveals a key feature that the expansions of the universe starts to accelerate as dark energy dominates. Now, we back to the one of the most philosophical equation. Will the universe end? And if so, how? Now, to answer this, we examine a realistic case, that is a universe that is a flat universe, matter dominated at early times and currently dominated by dark energy. Now, the first Friedman equation in this scenario will look like this. A dot over a square is equal to h0 square times omega m times a to the power of -3 plus omega lambda. By the observation, we have that omega m is nearly 0.3 and omega lambda is nearly 0.7. In the early universe, the terms omega m times a to the power of -3 term dominates, leading to decelerated expansion. But as the a as a function of t increase, the terms fade and the constant omega lambda takes over. Now, this causes the expansion to accelerate, a phenomenon confirmed by observing distant supernova and the cosmic microwave background. What happens next then? When the dark energy domain dominates, we see that the solution behaves like a to the power of t. A as a function of t is proportional to e to the power of ht. This is called exponential expansion. The universe grows faster and faster forever. Now, since the universe is expanding or grows faster and faster forever, this leads to a scenario known as the Big Freeze, where galaxies drift apart, stars burns out, matter decays, and eventually the universe becomes cold, dark, and empty. It is not a dramatic collapse like the Big Crunch, nor a catastrophic tear like the Big Bang or a Big Rip, but an endless fade into the silence, where a universe that doesn't die in fire but in frost. Now, from the paradox of a dark night sky to equations that describes cosmos, we've seen how mathematics doesn't just explain the universe, but it also foretells its fates. Now, thank you everyone. Wassalamualaikum warahmatullahi wabarakatuh.